Yeah, so we work a lot with environmental scientists. As I said, being part of this community, we want to kind of understand the emerging challenges in contamination. And this was a story that really grabbed us. It was a headline, Prawn to be Wild, and the shrimp and kind of prawns in the UK waterways are bioaccumulating cocaine. And it was kind of it's a sort of interesting academic project, but it points to a much bigger issue, which is that our waterways are very polluted, and anything that bioaccumulates is starting to bioaccumulate up the food chain, and that ultimately has really serious implications for people and animals. And so there are a lot of very, kind of unexpected revelations when you start to look into these problems.
We wanted to focus on kind of the most acute problems in water treatment, the few compounds that have a really outsized impact on our environment. And so we looked at certain classes of fluorochemicals. On the right here, they're collectively called PFAS, poly and perfluoroalkyl substances. They're used very widely in a number of applications. And the areas they're manufactured in the US, China, and Europe, they're very contaminating to the water. So they're used in Teflon, in Gore-Tex, in fluoropolymer production, in firefighting foams, in paints. They're additives to lots of industrial processes and lubricants. They're manufactured by a variety of chemical companies, and this is one of the towns, Parkersburg in West Virginia, where they have a chemical plant, and contamination of their water supplies was directly linked to 30 deaths and 300 instances of cancer. So that was incredibly serious. We've been to visit here. We've talked to some of the plants, and they're really in desperate need of better treatments. Because of that contamination there's been massive tightening of regulations, which is great. I'd urge you to Google PFAS if you haven't heard of them. There's so many stories coming up around the US, Australia, Europe particularly, where they're manufacturing these, and there have been instances of contamination. But they're very difficult to clean up. They're a key constituent of high-performance firefighting foam as well. So military sites, oil and gas installations, areas where they use foams, airports as well, they have a lot of treatment requirements. And so we kind of took a very problem-first approach. We had some technology around producing bio-based polymers and bio-based materials. We wanted to apply it to a water treatment problem. And so we had a look at kind of what the engineers are doing. We've heard a lot about engineers coming in and giving us inspiration as biologists and bioengineers. We kind of wanted to try and go the other way and think, what can engineering learn from biology and biological approaches? And so my engineering colleagues get very excited about this sort of thing, tanks and pumps and large-scale infrastructure. This is activated carbon. These are tanks that are used as the final step of most water treatment processes. If you want to clean fluorochemicals, you need something like this, massive installations with huge quantities of activated carbon. The high-quality carbon that goes into these tanks is derived from coal. With our process and with a kind of more biological approach, we have developed a leading product that uses a cellulose-based material. We get cellulose from agricultural waste, and with a bio-inspired process, we convert that into a granular material that is a drop-in replacement for that carbon and can more specifically capture fluorochemicals. We've talked a lot about sustainability, and are things really sustainable? Obviously, we have some chemical steps in our process, and we need to be very careful about how we do that. But we're replacing something that is made from coal at the moment, or there are some synthetic petrochemical resins, and we're replacing that with a kind of plant-based product that we've developed using bioengineering approaches. I really like this slide. This is my favorite slide, and this is not the first Pac-Man you've seen today. It's a very common metaphor in biochemistry, and I'm sure this sort of picture is very familiar to people in this room. It's not familiar when we go and talk at water conferences, when we go and talk to chemical engineers. For us, we think about specific binding interactions and designing those very precisely. And so this is our process. We take porous granules. I got very excited yesterday by some of the talks talking about design of experiments. We have a kind of DOE-style process where we do high-throughput screening to adapt and design receptors that's very much inspired by kind of drug discovery. It's the same process for screening, and we have 96-well plate format, and we use the facilities, and we're getting towards the automation. We work with Seaspiricy a lot on developing that. It's the same process if you want to make a drug, or if you want to make these kind of agrochemicals we've heard about, or if you want to make a cell line, you can use it to make a material. We have some additional advantages from that in that we can make our material regenerable. And so because we can design that binding interaction, we can also design it to change under different pH conditions or osmotic conditions. And so when we have a tank of material, you can capture the polluted, so you trickle the water through, the pollutant sticks to the material. You can then backwash with a solution with a different pH, say, release the pollutant in a concentrated format for disposal. We obviously, a lot of presentations have slides like this. Under the right conditions, we vastly outperform the conventional adsorbents. I don't want to do down the engineering, though. There's still, engineering is hard. There's still a lot of engineering to do. This is a really big market. Water is pretty vital to everybody. And I'd certainly encourage more kind of biotechnology companies to think about applications of their technology beyond the usual biological areas. We're initially cleaning these fluorochemicals, but cleanup of emerging contaminants is massive, kind of $30 billion estimated market per year for treatment technologies. We're hiring. Get in touch if you're interested by anything I've said today. Thank you very much.